Advent of Code 2025, day 8. This is OXDF. Let's take a look. So we're dealing with these junction boxes, which are basically like things that can be connected together with wires. And we get a bunch of 3D points that represents where they are in space. And so we need to, in the example input, I got 20. I expect it's gonna be a lot more in the puzzle input. We need to find the ones that are closest together. And so we're gonna actually work, if we think of like all the possible connections between every point, we need to start with the two closest together points and we're going to connect them with a wire. And then we're going to do the same thing with the next two closest points and the next two closest points, etc. And we're going to form a series of circuits. So like if A is connected to B and B to C, they're all in one circuit. And so we're going to do that in the example input. I hate when they do this with different sizes. We're going to make the 10 shortest connections. And in the real input, we're going to make the 1,000 shortest connections. Then we're going to find the 3 largest circuits. So the 3 groups that have the most connections, and we're going to multiply them together and get a result. And we're going to do the same thing for the puzzle input. So let's jump over here and my GenDay script for day 8. I go over this in video 1, but basically it pulls my input, it creates me an example file, which I should go grab some examples. And it creates a Python stub for me to work out of. Cool. Let's take a look at the real input. Much bigger numbers. That shouldn't matter much, but also 1,000 instead of 20. So a lot more points. And when we start talking about like each point can connect to every other point, that the number gets larger. So, all right, let's go through this in order. So the first thing we need to do is we're gonna have a list of lines. We need to really turn this into a list. We need to turn this into points with integers and everything. So we'll say for line in lines. I wonder if we can do this in 1. I'm gonna break it for a second and say we'll call this points is equal to, I'm gonna make it a list for now. Might need to change that. Points dot, let's see, x, y, z is equal to line dot split. They were all commas, yeah. Okay, split on comma. And then we're going to map int like that, and that should give us that. And we say points. I can spell. There we go. Dot. Wow. All right, then we don't go points dot append x comma y comma z like that. So now I should have my list of points. In fact, we can come here and do. Wow, points is a tough word for me to type apparently. UV run day 8 example, and we should have points that look like points. So now we have integer points. That's okay. So now we're just gonna brute force and get all the distances. So we're gonna say dists is equal to, again, I think I'm gonna do this as I don't think we're gonna be referencing back into this. We're just gonna need to loop over it by distance. So we're gonna work for now, or at least we're gonna say for what's the best way to do this? We're gonna get an x. We need to loop over both. We're gonna need to loop over twice to get all the points. So we'll do, we could reference points by their XYZ. I'm going to reference them by their index in this points thing. And that'll just be easier to, I can always go and get, like if I got this point right here, point 2, I can always go get the distance of parts of point 2 if I need it, but I'm just going to reference it by that. So we're going to need to enumerate. So we're going to say for n comma x1, y1, z1 in enumerate points for m comma x2, y2, z2 in enumerate points. I could do things like points from n onward, but this is not a big enough number that I need to worry about being efficient there. I think we'll say if, we only want to count it once. So we're going to say if n is less than m, because otherwise we will count it the other way. Then we can say dist is equal to, let's see, it's going to be x1 minus y1, x2. So what's the easiest way to do that? Squared, I guess, like that. That should work. Plus cow y1 minus y2 comma 2 plus now z1 minus z2 comma 2. I could take the square root here. I'm not going to bother because it doesn't, no point in it. I don't need the exact distances, at least anywhere yet. So we're not going to worry about that. So now I think I should have, I need to append this. So then we'll say dists dot append, and this is going to be dist nm. So we just need to know, we're just going to track the distance and then the index, the two indexes we have. This will be much longer, but again, that ran fast. We can just make sure that we're running in reasonable time here. But that was not bad. We got enough. And so we have this distance and then the two things. Okay, so now we have the distances. We're going to talk about union finds. And union find, I got a video here I'm going to put in the description. I think I can even do a little thingy right here up on my screen. But I also just will go over this. I'll include both these links in the description. But basically, it's a structure where you can start off with everything in its own set. And then if you need to combine two things, you just basically we're going to create a list called parent. And each thing is going to start with the parent of it is equal. Like parent of 1 will be 1, parent of 2 will be 2, parent of 3 will be 3, etc. And if I want to join 1 and 2 together, I just set parent of 2 to be 1. And so then there's a few functions you need. So to make a set, you just to put something in a set by itself, you just set it to its parent. If you need to find what set something's in, basically each set will have a representative node that is like, so in this case, the representative of this set is 1. And so if you search for 2, you'll find 1. If you search for 1, you'll find 1. And so when you define a set, we put 1 in here. If 1 is equal to parent 1, which it is, it just returns 1. If not, then we're going to say, what is the find set of 1? And then, so if we put 2 in here, it's not going to be equal. We'll come down to a find set of 1. Now we call again, and 1's parent is 1. So now we know we're done. And so that's how we can sort of put everything in. We can group things. And then to merge two sets, all we need to do is get the representative node of each of them. And as long as they're not equal, which if they are equal, then they're already set, we just set the parent of B equal to A. And so effectively what that's doing is, again here, if we need to merge these two sets, we find if we want to merge 4 and 1, we find the parent of 4, which is 3, and we set that equal to 1, and we're done. And now we have sets. So I hope that makes sense. This video is good and worth watching if that didn't make sense. But let's go ahead and do that. So first thing we need to do is we're going to create the parent. So we're going to say parent equal to, what's the best way to do this? It is going to be, we need to take in a, I go back here and show, where's my code? So we need to set for each item, each I and j. So for every number from up to the length of the points, we need to set parent of that equal to itself. So we're going to say parent is going to be a dictionary. We'll say for I in range. I can play this in one line. In range len points, and we'll say parent of I equal to I. We can probably say this. Actually, we can do this in one line. We'll say boom, boom, and then we just need to do key comma value. So I comma I like that. I think that'll do it. We can do parent here, and I'm not sure why that's failing. An indent. Weird. Parent of I is equal to, what did I do? Oh, whoa. I don't know how that got turned down. There we go. That looks better. And so now you can see 0, 0. Everything is just its own thing. So now we need our def. Let's make our find set of V. And that is going to, we're going to say if V is equal to parent of V, turn V. Otherwise, oh, and there's one optimization I'm going to show in this thing. So we can have these complex trees, but basically as you're kind of looping through a tree, it's better if you just sort of update, if you constantly are updating it so that the tree gets squatter and wider, and that way you have less searching to do. So basically, every time I search for something, I'm going to find it, and I'm going to just set the parent there as well. And that's just going to sort of shrink the tree up as we do it. So we will come here and say parent of v equal to find set parent of v. So we're basically gonna get the parent. We're gonna just move all these up to the basically we're gonna say every node that we find in this tree, we're gonna set it so its parent is equal to the representative node. And then we can return parent of v. Now we're gonna need to make def merge sets, and we'll call this like a comma b. I think that's what they call it here. Yep. Okay. And for that, all we're gonna do is we're gonna say parent of find set b equal to find set. So we merge two sets. We just get the parent of b, the representative node for b, and we make it to parent a, and now they're in the same thing. So now we can loop over distances. So we'll say, what's the best way to do this? We need to. I want to test on the example and the regular. So we're going to do. For now, I guess we'll just say wire count is equal to 10. Is that what we said in the example? There's only 10 wires. After making the 10 shortest connections. Okay. And we'll just leave that for now. And we'll say for I in range. No. Okay, we're going to loop over the 10. So we'll say for, I'm not sure what, something in sorted dists. And I need to properly enumerate that. So let's see, we need to get, no, okay, sorted dists. And this will be wire count. So that'll give me the first 10. And this is really not going to be X. We're going to want to do D, comma, and then this will be in dists, it'll be N and M. So we'll call, or I and J, or however we want to call it. We call it N, M. So we have our distance and our 2 points. And now for each of those, we are going to put N and M in the same, we're going to merge N and M. We're going to say merge N, M. Well, it's not merge, it's merge set. Sets. So now we've merged the first 10 sets. And now we need to get the size of all the sets. We'll say sizes is equal to, what do I want? This is going to be a default dictionary from collections, import default dict. And the reason, what we're doing here is we don't have for any point, we have a good way of finding its representative node. But we don't have a good way to say like, hey, for any point, what's the whole set that's here? And so what we're going to do is we're going to say sizes equal to default dict int, and then we're gonna calculate the size of each one. So we're going to say for, we want to go over all the p's. Yeah, actually we're going to do for x in range dot len points. We're going to go over every point, and we're going to say find set of x, and we're going to say sizes of that value. So get the representative node, and we're going to say plus equals 1. Basically, for every point, we're going to find the representative node. We're then going to increase. We're going to have this thing that shows us the sizes where you give it a representative node, and it gives you the size of that set. And so we just increase that size by 1 because it's a default dict. We don't have to worry about the size, and boom, we're good there. And so now we can say, I guess we'll do math.prod from math import prod, and now we can say prod sorted sizes 3. I think we actually want minus. Sorted going to give us the smallest large. Okay, we'll try this for a second. Part 1 is equal to that. I think this is not going to work. I think I've got my list wrong, but let's just run it and try. 6 is definitely wrong. I think, what if I do from -3 to the end? Oh, that was way too big, I think. So let's just do, let's say part 1 part 1 equal to sizes. So we have a default dict. We have 14. We have, okay, so this is the one representative node 14 is 4. Oh, okay, we do have, I think we're sorting by the wrong thing. So we need to do sizes dot values. Values, let's do that. And that should be a there. So let's just run this. Nope. Get rid of you. We're gonna come back to it. Okay, so that gives us our values. We do sorted sizes dot values. We should have, and we'll do comma reverse equals true. Now we have 5, 4, and 2, which are the biggest sizes. So we're doing better here. Now we can say prod, and that will be the first 3. And so we should get 40. Boom. All right. Now, to make this work on the puzzle input, we need to do this. If len points is less than 100, else 1,000. I think that's going to work. So basically, we're just changing the wire count based on the size of the input, because our example is 20 and our other one's 1,000 or something. So now we should be this. Everything else should be the same. So let's give it a try. We got a number. Let's go see how we did. Yes. All right. Let's read part 2. Okay. So part 2. We need to connect them all into one giant circuit, and to do that, and then we need to know when that circuit is formed, what the last 2 boxes connected were, so we can multiply their x coordinates together and get the answer. We can't, to do this, before we ran to 1,000 and we stopped, we can't just run to the end and stop, because it's going to get, the full circuit's going to get formed long before we reach the end of the things. If we've got 4 points, we only need 3 wires to connect them, even though there's going to be 1, 2, 3, 4. There's going to be like way more distances measured. So we need a way of tracking, like, when did we get to the end? And to do that, we're going to think about, like, we need length of p minus 1 wires to connect p points. So we're just going to count the number of wires we put in place, and then when we get to that point, we'll stop. So let's go ahead and take a look. What we're going to do is we're going to refactor this loop right here, and we're going to refactor it so that we run to a different point. So let's actually refactor part 1 to run that way. So we have wire count. We're going to say for what haven't I used? I think I'm good for I. Yeah, for I, comma d, comma n, comma m in enumerate, because we're going to count this way. Sorted dists. That. So that'll replace this. And now we're going to say, so I, let's say we're trying to do 10, I 0 through 9 is going to be fine. So then if we say if I is equal to wire count, then we're going to do all the part 1 stuff. Well, let's just do it. Let's say do part 1 stuff. But for every time, we're going to say, now, before we just did merge sets. We need to track, like, are we actually merging 2 sets, or are they already in the same set? So we're going to say n rep equals find set of n, m rep equals find set of m, if n rep is not equal to n rep. Now we could just add our count. Oh, we should do a count next. So connections equals 0. We could just do, so we'll say we could do our connections plus equals 1. We could just leave it like this, but there's no, once we go through all the trouble of finding this, there's no point in merging them if they're already there. So we might as well push this in. And then we need to say if connections is equal to len points minus 1, we can say part 2 is equal to points of n. That'll be points of n like that. And then we need the first thing, so that's 0 times points of M of 0. And I think we want to break. We don't need to keep going. We might as well do, let's make our part 1 stuff still work here. So now we just need to do, we need to do all this stuff right here. So we can say that, and then let's put all of you here. Tab. So now we only do that once. Should we get our part 1 in time? And then we come down here and finish our part 2, and part 2 is done. We can put this up with here, so like that, and save. And let's run on the example and see. So we still got our 40. Did we get 25272? That looks good. We got a big number. The points are just bigger. Nice, we got it. So all we did here was basically we didn't stop after wire count, but we just put our check in at that point. And then so this is just handling part 1 here. And then for part 2, we're gonna just be careful about how we count our connections. And once we get to our our n length of p minus 1 connection, then we know we're done with that and we can exit. Cool, that wasn't bad. Let's see how Claude does on this one. Claude, we will AOC8, and I will make a video someday about how this works. It might not be till after the competition's over at this point, but we'll see. So we are getting we're making the directory already exists. We are getting the puzzle and the input. It's going to tell me a second that it already sees it solved, and the answers were great. It can't write the example thing. Hopefully it's smart enough to just skip that now. Nope, it's not. What are you doing? I told you to skip that. Need to go check and see why. I thought I told it to fix that. Okay, so now this is a union find. So it's already identifying the same thing, and it's writing lines. It's got an error. Okay, so it's having to say target connections, and it did a very similar thing to, well, we'll see it when we run, but those look like the right answers. And those look, that was faster than mine, I think. Are those right answers? Yep. So solved it in, I don't know why does getting the date take it so long? 54 seconds, looks good. Let's take a look at what Claude did. It looks to me like it's going to do, it looked to me like just looking at it that it was very similar to what I did, but we'll see here. Scoot this over, scoot it down. Code is a lot longer, but it ran the loop twice, it looks like. So, okay, so it's reading in the data. It is getting the boxes, and it's storing boxes as XYZ. It's very similar to mine in the map int. Now, again, we would have seen if it tried to read my solution. So it didn't do that. That's good. Let's see. So I've blend of boxes is n. It's going to loop over. It's doing that thing I said was smarter. So it's going to, rather than doing my check where I just check if I is less than j, or in my case, n and n, it's going to just loop from that point. That's fine. It's going to get the points. It's going to calculate the distance, and it's going to append the exact same as I did, a distance, comma, that. So now it's going to sort the distances, just fine. It creates a parent list. Parent is list of range and interesting. Okay. Oh yeah, I guess that's fine. I did it as a dictionary, but I guess you could do it as a list. Yeah, okay. And it keeps a rank. Interesting. Okay, I'm not sure what that's for yet. We have a find. It looks just like our find, I think. If parent is not equal to x, set it that way, and then return parent of x. Oh, that's actually, I like that. That's actually smoother than mine. I mean, it doesn't matter, but it's smoother. And then their union is more complicated. There is another, I come back over here. I didn't do this optimization, but there is another optimization here where you keep track of the size of things, or the index. I was a little confused by this one, so I didn't get too into it, but it looks like Claude is actually implementing that, which is kind of cool. So their union function's a little bit more complicated than ours. It returns true or false. Oh, to say if it's already in the same circuit or not. That's kind of nice. I wonder if I should be doing that. Because then I don't have to. Then I wouldn't have to do these finds. I could just check, which I bet they're gonna do. Okay, so first part one, it's gonna get target connections. Looks just like mine. weird that it picked exactly 100. Then it's going to loop through the distances. It's going to join them. It's going to count connections. If connections equals target connections. Interesting. I wonder if it's counting connections all along versus counting distances. And so it assumes the first 1,000, there's no connections that there's no shortest distances that don't join. I guess that works out. I'm a little surprised that works. But it got the right answer. So then we're going to do circuit sizes. It's going to do the same thing we did, except it's going to just use get instead of default dict. We've seen that in the past. It doesn't like default dict as much as I do. And it's going to print part 1. Cool. For part 2, it's going to do the same thing. If the union happens, so this is the benefit of their union. So I had to do check and see if they're different. It just calls the union and uses that to return true or false. If the union happens, then it's going to subtract the number of circuits, which is going to be n. Okay. And then when it gets down to 1. Okay. So with each connection, there's one less circuit. So, okay, that's fine because it starts off, and then when it gets down to 1 circuit, we break and we print the last. So, cool. Good job, Claude. All right, I'm going to call it here. Thanks for hanging out with me today. I should be back tomorrow. I have a little bit of travel this week, so I'm not sure if I'll be able to make videos on Wednesday and Thursday, or I might have them late, or I'm not sure what they'll look like. So, I will do them eventually, I promise, but I'm not sure. No. If you've made it this far in the video, you're probably looking for the next one, so it might not be on the right day. I hope so. I might be able to do it while traveling, but I'm not sure. So thanks for hanging out with me, and I'll see you next time. Bye.